For this problem, we have tangent to the 6th power x dx. So the first thing we can do is just split it up into tan to the 4th power x and tan to the 2x, right? To the 2nd power x, right? Because there's a difference. So we can use a trig identity to change it a little bit, right? So we can have 1 plus tangent squared x equals secant squared x. So we can take this expression, right? And for tangent squared x, we can do secant squared x minus 1, right? Because if I subtract 1 on each side, it'll be tangent squared x equal to secant squared x minus 1. So now since we have that, what we can do is multiply it across, right? So we can have tangent to the 4th x times secant squared x, and then tangent to the 4th x minus tangent to the 4th x. So now since we have that, once again, since we have tangent to the 4th x, we can split it into tangent squared x, tangent squared x. Keep this the same, and then for this one, use the same trig identity and make it secant squared x minus 1 for one of them. Multiply it again, right? So tangent squared x times secant squared x, and then tangent squared x times negative 1 will be negative tangent squared x. So for after all that, we keep that the same. We can multiply this negative 1 across the entire inside, so this will become negative, and then this will become positive. So after that, what we can do is we can leave this the same, but for this entire expression, take out tangent to the 4th x, right? Take out secant squared x, right? Because if we multiply this across, we'll get this, right? So if we leave this the same and just multiply this across, so secant squared x times this will get us this, secant squared x times this will get us this. So this and this are the same. Now since we have that, what we can do is, let me zoom out a little bit, we can take the integral, right, separate it into two different integrals, and then once again use the same trig identity to make it secant squared x minus 1 over here, and then keep all this the same, and then let me expand it even more. And so we can break this integral again into secant squared and then minus 1. And we can do that because it's addition or subtraction. In this case, subtraction. If it's multiplication, we can't. But in this case, we can break it up into two different integrals. So we have negative 1 dx right here, and then secant squared x dx right here. And we haven't changed this. So now what we can do is, for this expression, we can use u substitution. So we can say that u is equal to tan x, and du is equal to secant squared x. So this will be u to the 4th, right, because we're substituting in u. And then over here, it'll be u squared, right? And then since the secant squared is taken care of, it'll just be du, because du includes the secant squared dx. Over here, we just keep it the same. And then finally, we take the integral of this part. And so for here, we'll add 1, right? It'll become u to the 5th, and divide by that answer, which is 5. Over here, we add 1, which will be 3, divide by 3. Keep the negative sign. Over here, the integral of secant squared x is tan x, right? Because the derivative of tan x is secant squared x. And then finally, for 1 becomes x, because the derivative of x is 1. Keep the negative sign. And then also remember to keep the c, or add a c. And then we can't keep this in as u, right? Because since we did u substitution, we have to convert it back. So we plug in tan, so it'll be tan to the 5th x, and tan to the 3x, keep the 5 and the 3, and keep this the same, and then remember to add a c. Because that's an easy way to lose points. So I hope all of that helped, and thanks for watching.